Hi, everyone. We'll just give it a minute to let people continue joining, and then we'll get started. Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar session on chlorine disinfection and CT calculations. My name is Owen Volk from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics, and then we get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it in the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information that you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now, for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application, falling short on project funding, not sure where to start? EFCN is here to help. Submit a request through the link in the chat to receive tailored support based on your project needs. And on that note, we can get started. I would like to introduce our presenter for today, Gregory Pearson, Water and Wastewater Trainer at the Great Lakes Environmental Infrastructure Center. Welcome, Greg, and I will hand it over to you.
Thank you, Owen, and welcome everyone. Okay, there's the share screen. And I'll probably go off camera here to help us to be able to see the slides. Is my presentation showing properly, Owen?
Yeah, looks good.
Okay. Welcome everyone again. We're going to be exploring chlorine disinfection and CT calculations today. And I'm coming to you, like Owen said, from the Great Lakes Environmental Infrastructure Center. We're part of the national EFC collaboration. It's a nationwide project. And we're located in the Great Lakes region at Michigan Technological University. And we serve primarily that 6-state region, but we also collaborate in this national project. And we're going to jump right in. It's going to be kind of a fast-paced presentation. It will be recorded, but we're going to try to cover some major ground today. And I want to begin by kind of stimulating some of our prior knowledge here and look at what disinfection is. Disinfection, the definition is it's the inactivation and or destruction of pathogenic organisms in drinking water, and we do that to protect health. There's 3 main categories of pathogens that we're concerned with. There's bacteria, viruses, and protozoa. And the main things that affect chlorine disinfection are the concentration of chlorine and the contact time. Now, there's some other factors that can affect the efficiency of disinfection, and those are factors such as pH, turbidity, the temperature of the water, reducing compounds, and other chemical characteristics of the water. But for the most part, the concentration and the contact time are the things that we're going to have control over um, mostly to make sure that we achieve disinfection. Now, chlorine disinfection had a major impact on public health. Back in the US, back in 1908, Jersey City Waterworks was the first to begin chlorinating their water supply. And that was in response to a lot of disease problems that were happening. For example, typhoid was a major concern in a lot of US states. And this graph that you see on your screen that's not waterborne disease incidences, that's death rates. People were dying, and these are death rates per 100,000 people, 100,000 population. And so you can see at about 1908, it looks like we were having like around 26 deaths per 100,000 population, so annually. So you can imagine if you were in a city of 100,000 people and you read in the newspaper 26 deaths due to the drinking water supply, if that were to happen today, you can imagine that would just be outrageous, but that's what they were dealing with. It didn't happen until around 1945, where they finally got below 1 death per 100,000. And so that wasn't that long ago. And even before that, there wasn't really a realization that germs, the viruses and bacteria and protozoa in water was the actual cause of disease. So a lot of these developments are still fairly recent in our history. Today, we want to answer 3 essential questions. The first is a theoretical question where how do we understand the concept of chlorine dose, demand, and residual, and we're going to be looking at the chlorine curve for that. And the second category that we're going to look at is operational math, and we're going to put these in our fun learning funnel here, and we're going to be asking how do we calculate dosage and feed rates for the gas, solid, and liquid forms of chlorine. And finally, we're going to look at some compliance issues, and the question is, how do we evaluate CT values to achieve log treatment compliance for viruses and Giardia? And what we hope to come out with is some practical applications that you can use back on the job. Now here's that chlorine curve. If you look at the chlorine curve, the y-axis is chlorine residual, and the x-axis on the bottom is how much chlorine we're adding. And it creates a graph here, and that's a graph of total residual, total chlorine residual. Now, when we add the first little bit of chlorine, you notice there's no residual. What happened to that residual? It was used up by reducing compounds, things like iron and manganese that are dissolved in water. When we get to the second of the 4 main zones here, we see the residual rising. That's because we're forming chloramines and chloroorganics. The main chloramine that's being produced in this initial part is monochloramine, and it's we're increasing the amount of total residual, no free yet. Now in this third zone, we're adding more chlorine, but you see the residual has dropped down. Why is that? Well, it's because that monochloramine is being destroyed and it's being replaced by the weaker forms of chloramines, dichloramine and trichloramine. So we see the residual go down until we get to this break point here. And this break point is where we consider all demand to have been satisfied. So there's kind of 2 ways that demand, the term demand can be used. First of all, the chlorine demand, we can be talking about the reducing compounds, but we can also be talking about those nitrogen compounds such as ammonia and other organics that can bind with chlorine and create combined chlorine. Once we get to this 4th zone, all demand's been satisfied and we can begin to build free residual. There's free residual and there's a little bit of combined chlorine. Remember that graph, that red line is showing us how much total chlorine is available. And total chlorine and free chlorine are measurements that we conduct in the water to see what our chlorine residual is. If we look at this in a different viewpoint, we can see now we have some free chlorine residual and some combined residual, and those added together equal our total residual. And we're going to do a little problem here, looking at the relationship between these different types of residuals. And so here's our first problem. We have a dose of 1.5 milligrams per liter of chlorine. Now, milligrams per liter, that's the same as parts per million. That's what we use to measure chlorine dosage and residuals. So we're adding this dose of 1.5 milligrams per liter chlorine to a water, and we measure the free residual, and we see that it's 1.0 milligrams per liter. And we have a total residual of 1.3 milligrams per liter. And so the question remaining is, what is the demand from reducing compounds? And if we analyze this, we see we have a portion of that 1.5 milligrams per liter dosage. The dosage is shown on the left-hand side of your screen. And now we see a portion of that consists of free residual. Another portion is going to consist of the combined chlorine, and we know how much that is because we also are given the total chlorine residual. You see on your right, we have the total residual of 1.3. So we have a combined chlorine of 0.3. So now we have, we know our dosage and we know our total residual. How do we define the demand? How do we find the demand? We take the dose minus that total residual. 1.5 minus 1.3 gives us 0.2 milligrams per liter, and that's the demand. That's the part we can't actually measure with our chlorine test, but we can deduce it. And so we have found out what our chlorine demand is. We're going to also, we can represent this relationship in an overall equation. The 1.5 milligrams per liter is our 1 milligram per liter free residual plus our 0.3 of combined plus our 0.2 of demand. So let's test our understanding here in poll 1, and I'll ask Owen to please bring up poll 1. And what this is asking us here, we have a drinking water with a demand of 0.4 milligrams per liter, and we have a total chlorine residual of 1.7 milligrams per liter. Now this demand, we're talking about the reducing compound demand. So what was the total chlorine dose that was added? And I can't see the results, so on. You can read them off as whenever you'd like.
Yeah, absolutely. I have it running right now. So we'll give it another 15 or 20 seconds and get those results up.
And I might ask, as we're waiting, how is everybody following along so far? Are you able to hear? Are you learning from the presentation so far? Is everybody following along? And let us know in the chat if everything is going okay.
Yep, I have chats coming in and everyone's saying all good, and yep, it's going well.
Great, thank you, Owen.
Okay, so we're gonna wrap up this poll and share the results. Okay, so 15% of people said 1.3 milligrams per liter. 1.4 milligrams per liter was at 1%, and then 84% said 2.1 milligrams per liter. There was none for 5.7.
Okay, you guys are good. And here is a representation of that problem. Here's the total chlorine residual, 1.7 milligrams per liter, and that's the free and combined chlorine. And then we add on our demand, and our equation is dose equals demand plus residual, or residual plus demand. And so 0.4 plus 1.7 equals 2.1 for our dosage. Let's move on to feed rates now. We're going to begin with gas chlorine feed rate because gas is 100% strength. And we're going to use a formula called the pounds formula. And we use very particular units for the pounds formula. MGD, a million gallons per day. Milligrams per liter is same as part per million, and then we multiply that by 8.34 pounds per gallon, which is the weight of water per gallon. This equation doesn't really lend itself well to dimensional analysis because you see you have some MGD, then you have some metric units, and you have the weight of water. I'm going to show you a slide that will help us make a little bit more sense of it. But for first of all, we're going to use the formula and see how it works. But gas chlorine usually is read out and calculated in pounds per day. You have a regulator that controls the vacuum coming out of the chlorine gas cylinder. That venturi in the water line at the kind of the bottom middle of your screen creates a lower pressure, and it causes chlorine to be drawn in and mixed into a water flow. And that's controlled by a gas feeder that is the same as that regulator that's circled there. The top of this gas feeder is the regulator control, and we have a rotometer, which is a little ball that will float and indicate the number of pounds per day. And this could be from 0 to 40, which would be about the maximum amount of gas you draw from a 150-pound cylinder. So it might go from 0 to 40, or it might go a smaller range if you're going to be chlorinating at a much lower poundage. But as you adjust the needle valve, this little rotometer ball will float up to the feed rate in pounds per day. And keep in mind, when we use pounds per day in an MGD, that's a rate of feed. You can also use this pounds formula to calculate pounds for a volume, which then you would have your flow. You wouldn't have flow, you'd have volume. It has mg instead of mgd, but the equation works the same way either way we use it. We'll do an example here, and we're just going to plug in our numbers for this first example. So here's our question. What is the feed rate setting for chlorine gas if the plant flow is 1.2 mgd and the dosage concentration is 1.5 milligrams per liter? So we can basically just plug in 1.2 mgd for flow and 1.5 milligrams per liter for the dosage, and the 8.34 pounds per gallon doesn't change. So if we just plug it into our pounds formula, the flow in mgd times the dosage in milligrams per liter, 1.2 times 1.5 times 8.34, we get 15 pounds per day. So we can go to our chlorine rotometer and adjust it so that it reads out 15 pounds per day, and we'll achieve that ideal dosage that we're looking for. Now, I promised I was going to show you a little bit about the pounds formula. Here, I have a little exercise and some notes here. The MGD, we're looking at how many of these million-gallon units are there, and then the parts per million tells me how many parts of the chemical or the solid are in each of those mg's. You can also think of milligrams per liter as parts per million, or how many millions, and then of course the weight of water. So this pounds formula is for smaller dosages, and we're kind of assuming that everything is the same weight as water. And here's the problem we just did. 1.2 mgd times 1.5 milligrams per liter times 8.34 pounds per gallon equals 15 pounds of chlorine per day. Now, here's the concept. I'm going to take that 1.2 mgd. I'm going to show you something here. Instead of writing 1.2 mgd, I'm going to write 1,200,000 gallons. And I'm going to see how much that actually weighs. So I'm going to multiply that by 8.34 pounds for each gallon. And I get a total water weight here of 10,008,000 pounds. That's how much all that water weighs that flowed, that's going to flow through, throughout an entire 24-hour period for this equation. Then, if I were to rewrite 1.5 parts per million, or milligrams per liter, as 1.5 parts per million parts, or 1.5 millionths, if I take that 1.5 and divide it by a million, and then multiply it by that weight of the water, 10,008,000 pounds, I still get 15 pounds. So conceptually, you see what the pounds formula is doing. That dividing by the 1 million and multiplying by the 1 million has already been canceled out. So we're seeing the form of the equation after those 1 millions have been eliminated or cross-canceled. Does that make sense to everyone? Let me know in the chat if that is useful to understand how the pounds formula works. Also, the Pounds formula can be rearranged to solve for dose, which is very handy. How do we do that? You notice here's the dosage in milligrams per liter. If we wanted to solve for dose, on the right-hand side of that equation, we have MGD and 8.34 there. We want the dose by itself. So how would we get it by itself? Well, we would have to divide out the MGD and 8.34. And a little principle when dealing with formulas, what you do to one side of the formula, you have to do to the other side. So what we would do, we would divide both sides by the flow and by 8.34. And so we rewrite it like this. And so you notice how we're dividing both sides of that equation of the both sides of the equal sign by flow times 8.34. And on this right-hand side of the equation, you notice we can now cross cancel out flow and 8.34, so we get dose by itself. So if we rewrite it, flip it over and rewrite it, we see that dose in milligrams per liter is equal to the pounds per day divided by the flow in MGD times 8.34. There's another way, and by the way, Owen, did we get some confirmation that the pounds formula explanation was helpful, or was there dead silence?
We did get that.
Okay, good.
Yes,
Thank you.
we did get
I'm
that
glad you're
response.
all following.
Also, I'm just going to jump in really quick just to say, if you want to respond to when he puts those prompts out, feel free to put them in the questions box. That can serve as the chat for you.
Yeah, thanks, Owen. Thanks, Owen. So I know we're kind of separated by this format of webinar. So I'll check in with you guys once in a while, best I can. And so I appreciate your feedback, because we want to know that I'm not going too fast. Now we can also use a pi formula to calculate for the pounds formula. And what we do, we create a circle, we divide it in half from the top and the bottom, and then we create a little triangle that divides the bottom into 3 components. And how do we use this? We multiply across the bottom, flow times dose times 8.34, to get the top, the feed in pounds per day. So if we multiply across the bottom, you notice that's the same as the algebraic formula, MGD times milligram per liter times 8.34 pounds per gallon. And if we tried this with an example, a flow of 0.6 mgd and a dose of 0.9 milligrams per liter, we can actually write those right into the chart. For flow, we put in our 0.6. For dose, we put in our 0.9. Now we have 3 numbers on the bottom. We can multiply across the bottom, and 0.6 times 0.9 times 8.34 pounds per gallon. And I hope you have your calculators and you're following along with me, because I could make a mistake and you could catch it. I get 4.5 pounds per day. And I can write that right into the top there. And so then I have kind of a record of what I did to solve that problem. Some people like the pi formula. You can also use this to solve for dose. I'm going to show you how the same pi formula, that center line, can become like a dividing line. So if we put the same problem, but we leave out dose, and instead of the pounds per day, we have calculate the dose if the gas chlorine feed rate is 4.5 pounds per day. We'll put that in the top, and the plant flow is 0.6. This would be very similar to what an operator would experience. You know the dosage rate, the feed rate, and you know the plant flow, but what is the actual dose? You don't actually know that, because there's reducing compounds and combined chlorine. So we plug our numbers in, and we're going to solve for dose. So we're going to write the equation as dose equals, and we're still going to multiply across the bottom, but now we only have 2 numbers. Let me show you how that looks. Dose, and the 4.5 pounds per day is above the dividing line, so we put that on top. And on the bottom, we have the flow as 0.6 mgd times 8.34 pounds per gallon. And notice this is the same as the algebraic formula that we developed for dose. If we take 4.5 pounds and we divide it by that 0.6 times 8.34, we get the dose is 0.9 milligrams per liter. It's the same problem we just did, but we just rearranged it. So it's the same equation that we developed by dividing out the MGD and 8.34 that we discerned algebraically. Now we're going to go to our next poll and give you a chance to solve a problem. In this problem, the operator is there at a treatment plant and looks at the chlorine feed rate, and it's set at 30 pounds per day. And the plant flow, you can read the master meter, it's set at 2.1 mgd. we want to know what is the actual dose of chlorine that we're administering to this water source. And you have two ways you can do it. You have that formula that we derived algebraically, and you also have the pounds formula where you can use that dividing line concept. You guys are a good group. I see you're actively working on the poll, and I appreciate the feedback that you give us.
Okay, we'll give it another 15 seconds. I'm just gonna give it a few more. Just I see some responses still coming in. Okay, so we're gonna run to results now. So 77% said 1.7 milligrams per liter, 14% said 0.58 milligrams per liter, 33% said 4%, sorry, 4% said 0.33 milligrams per liter, and then 4% said 0.15.
Okay. Okay. Well, I designed it to have some trickiness in those answers, but now let's look at the solution here. So here we got the feed rate, 30 pounds per day, and the plant flow is 2.1 mgd. And so we're solving for the dose. So there's two ways you can do it. You can use this formula that we derived algebraically, and you could also use this this pie chart. So in the pie chart we could put the 2.1 mgd in the flow area and the pounds per day on top. Either way we do it, we end up with this equation that says dose equals 30 pounds per day feed divided by that 2.1 mgd flow times 8.34. When you do that multiplication on the bottom and then divide the top by the bottom, you end up with 1.71 milligram per liter. So most of you got it right the first time, and those of you who got something different, I appreciate you giving it a try, and this might be new math to you. And if you still have problems after you watch this presentation, if this is brand new to you, you're welcome to contact myself or anyone else in EFCN, and we'll help you. Now let's move on to the solid form of chlorine, calcium hypochlorite, and it's also called high test hypochlorite or HTH. So this is generally 65 to 70% strength, and you notice the top part of that equation is the pounds formula. What we're doing there, we're calculating how many pounds of pure chlorine would we need to feed, and then we divide on the bottom by the percent strength. That gives us the actual weight of material that we need. So we're going to need a little more weight of this material, more so than the gas, because it's not 100% strength. It's not pure. It's 0.65 to 0.7. When we divide by the percent strength, we're actually dividing by the decimal equivalent. So 65% is going to be 0.65, for example. Let's try one here. Now in this one, I'm going to use it for disinfecting a main. So instead of million gallons per day, I'm just going to use million gallons as a volume. And instead of pounds per day, I'm just going to use pounds. It's the same formula, but in this scenario where we have a new 8-inch water main, it's 500 foot long. We just installed it and we're going to disinfect it. And we're going to use a dose of 50 milligrams per liter. So the question is, how many pounds of 0.65% strength, or I'm sorry, the 65% strength HTH will be required? First thing we're going to do is calculate the volume of the water in that main in million gallons. And we're going to use a formula here. And I'll just introduce this formula if it's not familiar to you in C2 here as we're proceeding. The formula we're going to use for the volume of a cylinder is diameter squared times 0.785. That 0.785 is 1/4 of pi. So if we were using pi r squared, we would use, radius. But in this case, we're using diameter. So we use diameter squared times 0.785 times the length. And then we use this conversion factor times 7.48 gallons per cubic foot. So every cubic foot is equivalent to 7.48 gallons. The only way we can use that is we have to have all of our units in feet. So the diameter's in feet and the length's in feet. So diameter times length is the same as foot times foot times foot. That gives us a cubic foot. That's why we're able to convert it. Now, when we plug those numbers in, you notice I've converted the diameter of 8 inches to foot by taking 8 divided by 12, which gives me approximately 0.67 feet. So 0.67 feet times 0.67 feet is the diameter squared, times 0.785, then times the length, 500 foot, times 7.48 gallons per cubic foot. That gives, on the top, that gives me the number of gallons in that pipe. But I need my gallons to be not gallons, but million gallons. So I'm going to divide that by 1,000,000 gallons per mg. And what I get is 0.001318 mg. So that's the number of million gallons that are in that pipe. Now I can plug that volume into my calcium hypochlorite formula. And we know our dose is 50 milligrams per liter. So we're going to plug the volume in, the 0.001318 mg, that's our volume, times 50 milligrams per liter dose, times 8.34 pounds per gallon. Then you notice on the bottom, that top part's going to give us the weight of pure chlorine. On the bottom, we're going to divide it by 0.65 because it's 0.65, it's because it's 65% strength. And that'll give us the weight that we need of calcium hypochlorite. I'm not sure if any of you have calculated that yet. Is there any answers coming into the chat, Owen, for
I haven't
pounds?
gotten anything yet.
I'll give it
30
seconds if somebody wants to try it.
I just had one come in and said 0.837.
Okay, that sounds pretty good. I rounded it up to 0.85, but it depends on how many decimals you keep for the mg. But I think that sounds like that person got it exactly right. So 0.85 pounds of this calcium hypochlorite to disinfect this main, and that would probably be a dosage where you're disinfecting the main over a 24-hour period. Okay, great job, everyone. I know I'm not giving you a whole bunch of time for everybody to do the problem, but I appreciate just that one coming in. Now, as we move into the liquid chlorine, we're going to look at a couple of concepts here. First of all, a specific gravity. Water, by definition, has a specific gravity of 1. And when we're calculating specific gravity, we're looking at the ratio of the weight per gallon of a substance to water. For example, we might calculate the weight of 1 gallon of 12.5% sodium hypochlorite. That's a very common strength, 12.5% strength for a liquid bleach. And it has a specific gravity of around 1.2. So how would we know the weight of that? Well, we would take 1.2 times the weight of water, 1.2 times 8.34 pounds per gallon, and we'd find the weight is around 10 pounds per gallon. So it's a little heavier because it's a little denser. Now, when we look at the equation for calculating feed rates for the sodium hypochlorite, you see we still have the pounds formula on the top. We have the percent strength on the bottom. We just dealt with that with calcium hypochlorite. So that top part is calculating the weight of pure chlorine we need. The percent strength is converting that to the weight of the material that we need to deliver that much chlorine. And now we're dealing with something that's only I keep saying point, it's 12.5% strength, or 0.125. Now this additional figure, dividing by the weight per gallon, is gonna, instead of having pounds that we need, it's gonna give us the result in gallons per day. I'll give you an example here also how the total equation would look. Instead of just weight per gallon, we're going to include that specific gravity times 8.34. So whatever that chemical is, it will have its own specific gravity to convert the pounds into gallons. And we'll do an example here. Here's an example. What is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 0.5 mgd and the dosage is 0.9? And we're going to try this. We're just going to plug in the numbers and see how it works. So there's our equation. Flow times concentration times 8.34 on the top. Percent strength, we're going to use the decimal equivalent. And then we have times the specific gravity times 8.34. That those two combined, the specific gravity and 8.34 is the weight per gallon. So if we plug all those numbers in, and if anyone wants to shoot the answer into the, I guess the question pod is what Owen has us using. You can feel free to put the answer in. But here's our equation: 0.5 mgd, that's our flow, times 0.9 milligrams per liter times 8.34 pounds per gallon on the top. And then we divide by that percent strength. 0.125 is the decimal equivalent of 12.5%. And then we have times the 1.2 specific gravity times 8.34 pounds per gallon. Any answers come in, Owen?
Yeah, I've gotten a bunch, and they have all more or less unanimously said 3.
Great, great job. 3 gallons per day. And so we would calibrate that with our chemical feed pump to deliver about 3 gallons per day. Great job, everyone. Now, another thing that we need to know is how to calculate contact time. We may be familiar with theoretical detention time, which is just the volume over flow. And that's theoretical because it assumes that there's no short circuiting. But contact time, we'll use a baffling factor that accounts for short circuiting because the tank doesn't have perfect flow unless it's a pipeline. A long, narrow diameter pipeline is considered to have perfect flow. The baffling factor would be 1 for a pipeline. But here's what the equation looks like. To calculate disinfection contact time, you have the volume of the basin in gallons times the baffling factor, and then you divide by the flow in gallons per minute. You notice you have gallons on the top, gallons on the bottom. The only thing that's going to be left over is time in minutes. So there's a range of baffling factors from basically 0.1 to 1. And so you might have a tank that doesn't have very good baffling, where you see the incoming flow has a way to make a straight shot to the outgoing flow. So that would be a definition of short circuiting instead of occupying every possible space. And this example of a tank might be something that's considered unbaffled to poor baffling. It would have a baffling factor between 0.1 and 0.3. In other words, you're only getting between 10% and 30% use of that volume. You might have something that's a little better. You see this tank diagram at the bottom. There's some serpentine action and some baffles it's directing the flow. And so we're getting a little better baffling. So that might be something between average baffling to superior baffling. And that perfect plug flow would be reserved for pipelines. And this is something that you would work with primacy to figure out your disinfection clear well. How well is it protected from short circuiting? Now here's an example here. We're going to calculate the disinfection contact time for a tank that has a volume of 75,000 gallons, and we're going to say it has a baffling factor of 0.5, and the flow through the tank is 500 gallons a minute. So if we put our information in our formula, we have the volume 75,000 gallons multiplied by that baffling factor by 0.5, and then we divide that by 500 gallons a minute. I'll give a second again if anyone would like to provide the answer to that before I reveal it. No takers, Owen?
Oh, we have a bunch. Sorry, I was responding. Someone, there are a lot of 75
Okay,
minutes as the
excellent.
response.
Good job, everyone. So 75,000 times 0.5 divided by 500 gallons a minute. So we have a total contact time of 75 minutes. And that's going to be important as we're calculating our CT values. As we go into the compliance section of our presentation, CT values are used to compare to the required CT values for log inactivation. So we have 3 log inactivation plus removal of Giardia. So in other words, 99.9%, there's 3 nines, either of Giardia need to be either inactivated or removed. And then for viruses, we have 4 log. It means that 99.99% of all viruses need to be either inactivated or removed. The compliance is achieved by a combination of the two, removal and inactivation, or filtration and disinfection. So total. And there's some considerations though to mention. So you notice if it's either or it's a combination, you could achieve all of that with inactivation, or you could achieve all of it with filtration theoretically. But that probably would be a problem if you were just leaning on one or the other, because you'd be depending on just one barrier, and you want to make sure all of your multiple barriers are robust. So you have a robust removal, you have a robust inactivation. And speaking of multiple barriers, you have source water protection, coagulation, flocculation, filtration, disinfection, and then finally testing and protection of the water system from sanitary defects, because your operators are out there monitoring and repairing. There may be a need to chlorinate less if you have disinfection byproduct problems. So there's a balancing act here. And some other considerations, there may be some specific requirements of your primacy agency that they want you to achieve, and also the plant design will depend, that'll affect how many removal credits you actually get. It's kind of a standard practice to allow a certain number of removal credits depending on the plant design, how well it's working. A common amount might be 2 to 2.5 logs for removal for a well-designed surface water treatment plant. For inactivation, we use tables. This is an example of a table for log 4 virus inactivation, and I'll show you kind of how it's used. We're going to be measuring the water temperature and the water pH. Now we're going to be using the minimum water temperature that we have, because we want to look at kind of like the worst case scenario, to make sure that every gallon of water that passes through our plant is in compliance. So the pH and the temperature, and you notice that the lower temperatures, disinfection is less effective, so we need higher CT values, where at the warmer temperatures we need lower CT values. Now we'll give an example here. We measure the pH and temp, and we find out the temperature is 16 degrees and the pH is 7.5. So we're going to be looking at this pH range of 6 through 9 and this temperature of 15. We're going to go slightly below that 16. It's possible to interpolate between these, but another technique is just to use the next lowest temperature. You wouldn't want to use a higher temperature. You'd want to use a lower one, because you want to make sure that you're achieving compliance. So in this case, the table indicates that we would need to achieve a CT value of 4 or greater to have compliance with the 4 log inactivation of viruses. And I'll give an example here. We have a small groundwater system, and we have a chlorine residual of 0.8. We're measuring a free chlorine residual of 0.8 at the end of the process. And our contact time is provided by a 3,500 gallon pneumatic storage tank. The baffling factor is not that great, it's 0.3. And the maximum flow through the tank is 200 gallons a minute. And we want to look at whether this system is attaining enough, high enough CT value to attain that 4 log virus inactivation when the temperature is 16 degrees and pH is 7.5. Same factors we just looked at. So first of all, we're going to look at the contact time. So we're going to calculate that contact time. We have a 3,500 gallon tank, a flow of 200 gallons a minute, and a baffling factor of 0.3. So 3,500 gallons minus that times that baffling factor divided by 200 gallons a minute gives us 5.25 minutes. So we're going to take that number of minutes and we're going to multiply it by the free chlorine residual of 0.8. 0.8 times 5.25 gives us 4.2, and then we have some strange units here. We're taking milligrams per liter times minute, so we can say milligram minute per liter if we wanted to have a unit for that. But our CT value is 4.2, and then we're going to compare with the required CT value, and we already determined that we needed to achieve at least 4, and we've exceeded that. So we're actually in compliance. We've met our CT requirements for 4-log virus removal. And now we're going to move into Giardia. But before we do, we'll talk briefly about the effect of pH. pH is a bigger deal when we go to the Giardia. Giardia is a little, it's more difficult to achieve 3-log Giardia inactivation than it is to achieve 4-log virus inactivation. Now you see a chlorine curve here where it's showing how free chlorine exists in the water depending on the pH. At the bottom, you see the pH ranges from 5.5 all the way to 10, and you see the percentage, how it's existing in the water as either hypochlorous acid, the HOCl, or the hypochlorite ion, OCl minus. So you notice here, it can exist as one or the other depending on the pH. Hypochlorous acid is preferred. It's more effective at oxidizing pathogens. And I'll give you an example how to read this chart here. Let's look at a pH of 7. If we look at a pH of 7, we see that it's about 80% hypochlorous acid and about 20% hypochlorite ion. So a pH of 7 gives you a pretty good scenario. There's some things that you could do. If you had a high pH, you would probably have to add more chlorine and have longer detention time. But you can also see that there could be a possibility of adjusting the pH down so that you have a more effective disinfection process. And we're going to do a problem here, and you're going to get to calculate the CT value for this in a moment. But here's our problem. We have a flow of 800 gallons per minute water, and we have a free chlorine residual. We always measure this chlorine residual at the end. It's the minimum chlorine residual. 800 gallons of minute per minute flow of water, free chlorine residual of 1.2, and we have a 75,000 gallon clear well. And this one has a better baffling factor of 0.7. So here's our clear well, our 800 gallons a minute going in, and there's our volume and our baffling factor. And so when Owen brings up this next poll, I want you to write something down first, so before he brings it up. Jot down on a note paper, our flow is 800 gallons a minute. The volume is 75,000 gallons, and the baffling factor is 0.7. Then we have the free residual of 1.2 milligrams per liter. So you're going to be needing to calculate the contact time, the disinfection contact time, and then multiply that by the free residual in order to solve the problem. And there's also a pH of 7 and a temperature of 15 degrees Celsius. We'll use those later when we look at our table. So go ahead and bring that poll up, Owen, and I'm going to ask you to calculate the CT value for this problem.
All right, it's up and running. I'll give it a little bit.
You guys are a good group. I appreciate the interaction and your willingness to try these problems as we're going along.
So just a heads up, this might be a bit skewed. It seems like the numbers are different between the last slide and this problem of the
Oh,
poll. I've been getting some responses on that.
oh, sorry about that, guys. Well, I guess that's my mistake. I think I must have sent Owen the poll along, well, maybe not a long time, but I must have revised it and not revised the poll. How different are the numbers, Owen?
I can read you the question. It says 800 gallons per minute water with a residual of 1.2 milligrams per liter enters a 100,000 gallon clear well with a BF of 0.07.
Oh, 0.7, right?
Yeah.
Okay, so um, all right, we'll look at the results from both angles. Sorry about that, everyone.
Okay. So now we've had an extra amount of time with it. I'm gonna just close it up and we can review what people have chosen. So based off of this question, I'm assuming 4% of people said 150 milligrams per minute over liter. 50% said 105, 31% said 87.5, and then 15% said 72.9.
Okay, great. And let me just talk through this here. Now, it was on the poll, it was 100. The only difference was it's 100,000 gallons, right?
Yes.
So if I were to do that, 100,000 gallons times 0.7 baffling factor gives me 70,000. I divide it by the 800 gallons per minute. That gives me 87.5 minutes. And then I multiply that by the 1.2 milligrams per liter, and that gives me 105. So 105 would be the correct answer for that. So back to this problem that we have in front of us, we have the 75,000 gallon. I'm going to show you the solving of it. It's that one number was different, but the procedure is still the same. So let me show you how we would solve that here. The contact time is the volume times the baffling factor, and we divide it by that 800 gallons per minute. Now in this case, we're putting the 75,000 gallons. It was 105 minutes, but reducing that volume from 100,000 to 75,000 gallons, it removed about 40 minutes. It made a pretty significant difference, didn't it? So 75,000 gallons times 0.7 divided by 800 gallons a minute, 65.6 minutes. So then we can take the CT value by taking the number of minutes and multiplying it by the dosage. 1.2 milligrams per liter times 65.5 minutes equals 78.7 milligram minute per liter. Okay, it's that we had a little bit of a variation there, but is everybody still with us? Is everything okay? Let me get some confirmation from Owen that everybody's on the right track.
Yep.
We had
Getting responses that people are all good.
okay, we had a little learning moment there. That's the Pearson experience. I always have something like that that I forgot I changed. So sorry, I apologize for that. Now the next step is to compare with our table. Now we are looking at the 3-log inactivation. Now here we had the water temperature, and we're going to look for a table that is associated with 15 degrees Celsius. So there's different tables for different temperature ranges. Now our pH is 7, and our chlorine residual is 1.2, and we're looking at a table that's 15 degrees. We're looking for the pH of 7, that section of the table, and then we're going to look at the 3-log inactivation. And then we're going to draw a line here, but from our 1.2 milligram per liter concentration over to the 3-log inactivation, and we find that we're going to need a CT value of 76 at least. And we just calculated that we achieved 78.7 with that 75,000 gallon table. So that exceeds the minimum of 76, and so we achieved compliance. Now with our 100,000 gallon tank, we really exceeded the compliance. So that's I think that actually is that I think I'm learning from that because the larger basin gave us more contact time, and so we really exceeded that minimum required. Now finally, as we wrap up here, there's an equation I want to introduce to you, and it's a way to calculate the log inactivation for in this case we're looking at the 3 log inactivation for Giardia, the 99.9% inactivation. And so the equation is 3 times the CT value achieved divided by the CT value required. Now, I want to explain this equation. If we achieved 76 and we were required to get 76, that 76 divided by 76 would be 1, right? So 3 times that 1 gives you 3 logs. That's why that 3 is there. So as an example here of the equation we just did, we achieved 78.7 and we were required to achieve 76. So 78.7 divided by 76 and then times 3 gives us about a 3.1 log inactivation. Now remember, we may also have credits that we can use from the plant's removal processes. So for example, a plant might have a credit for 2 log removal, 2 log treatment for removal. So the total treatment in this case, if that were the case with this situation, we'd have 3.1 log inactivation plus the 2 log removal. So we would have had a 5.1 total log treatment. Now, you may have a situation where you're targeting a lower inactivation log because you're trying to minimize disinfection byproducts, or maybe there's an inability to get the chlorine high enough, or there's not enough mixing time. In that case, you may be achieving your overall compliance by adding that inactivation log to the removal log. For example, if you achieved 1.5, you'd add that to the removal credit, 1.5 plus 2 removal credit, to get a total treatment of 3.5 logs. So that's how you look at it. If you needed to increase that, there's the ways that you would increase it would be either increasing the residual, improving the baffling, adding additional clear well volume like we did in my little error there. You could also decrease the pH of water. If you had a higher pH, decreasing that pH of water actually reduces the CT value that you need to achieve, and it makes disinfection more effective. And the last poll here, I'm going to have you calculate overall CT compliance using that formula here that's shown on this screen, the 3 times CT achieved over CT required. So Owen, go ahead and bring that poll up.
I just had a quick question come in that I think I'm going to ask right now just because you have the equation up. Someone was wondering where the 3 comes from in the equation.
Yeah, that just that helps you to have 3 logs. So remember that chart, it was 3 log removal. So the CT that was required for 3 log removal was 76. So if we achieve 76, we'd have 76 over 76 would be 1. And so we would achieve it. And because that means we've achieved 3 log inactivation, we simply times it by 3 because we achieved what the chart said we needed for 3 log inactivation. Does that make sense?
Awesome. Thanks for sharing that. I'll let you know the response. I'm going to launch the poll now. Okay, give it another 10 seconds. Okay, so results wise, 3% said 0.52 log, 0.52. 19% said 2.75 log. 25% said 3.50, and 52% said 4.75 log.
Okay, great. Let's look at the answer here. Here's our solution for the log activation that we achieved through disinfection. We achieved 60 and we needed 80, so 60 over 80 times 3 gives us 2.25 logs from inactivation. Then we added on our 2.5 log removal credit. So 2.25 inactivation plus 2.5 for removal gave us 4.75 logs total. I want to thank you all for attending today. There's additional resources in your slides. If you download the slide handout, you'll have these links for relevant information about doing these types of calculations. And I also included some drinking water regulation references there, and a nifty pipe disinfection calculator that I thought was kind of cool for disinfecting pipes. I want to make you aware that efcnetwork.org is a location for funding guides, and you can request technical assistance and find all kinds of tools, register for other events like this. And if you wanted to visit us at the Great Lakes Environmental Infrastructure Center, the website is gleic.org, and you're welcome to contact me. It's pretty simple email, gpearson@mtu.edu. If you have additional questions or would like to talk about some of the material we covered today, you're welcome to email. And I want to open us up for questions. And if you'd like to share one thing you enjoyed learning about in the chat, I'd like to hear about it.
Okay, so I do have a quite extensive list of questions. Just so everyone knows, slides will be sent out in the follow-up email. You can also download them through the handouts tab now. We're going to try to get through as many of these questions as possible. Whatever we don't finish, we will also attach and send out with that email. Let's just quickly check to see if there's anything else. Oh, also, if you do need to go, I know we're going to be a little bit over time. If you do need to leave, that's totally fine. There will be the recording that you can catch the questions in after the fact. So the first question that I received was, what is the time frame for reaction when reducing compounds?
Oh, yeah, that's a good question. That's kind of a chemistry thing, but generally that's occurring in less than a minute usually. There is actually an interesting book that you can download from EPA, and it's actually the arsenic treatment technology handbook, arsenic treatment technology handbook, and they have an interesting section there on stoichiometric reactions. And they, even though it's about arsenic, they deal with some of this chemistry. And so normally it's less than a minute that those first reactions occur. And it could be even faster, but you're depending on how efficient the mixing is. So there's some factors, but as soon as that chlorine it comes in contact with a dissolved particle of iron and manganese, it's pretty quick. I'm not sure how quick. I'm not a chemist, but if anyone is a chemist online, you can feel free to join in the conversation here and let Owen know.
Okay, so the next question I got was, what is Venturi?
Oh, Venturi is a neck down portion in a pipe, and what you're doing is restricting the flow. So if say you have a 4-inch pipe and you basically neck it down like a cone and then back out to the original size. So it goes from 4 inches in diameter down to 1 inch in diameter, then back out to 4 inches. That would be a Venturi. And what that's causing is it's causing an increase in the velocity of the liquid. And the Bernoulli principle is involved here. When a liquid or a gas moves more quickly, it causes a decrease in pressure. That's the same concept with an airplane wing. Airplane wing is curved at the top, and the air has to go faster over the top than over the bottom, and it decreases pressure and causes lift.
Okay, next question. Someone was wondering that they assumed that you could use the same formula. This was earlier on for liquid chlorine, just using milliliters to liters after incorporating a dilution.
Um, I'm not exactly sure. Uh, I'm not sure. I don't understand the question fully, but
Yeah,
yeah, if
trying to
whoever wrote
find
that
what
question, if you
the
clarify to Owen, I'll try to answer it.
yeah, I think some of these are specific to certain of the formulas, but we can, if I figure that out too, I can also pass that along
Yeah,
to
sorry.
get a response. Okay, so someone was wondering, does pounds work for smaller septic systems like 450 GPD in
For
that like
small
range?
for smaller septic
Yes.
systems,
Yes.
for pounds. Well, let me say it this way. You can use the pounds formula to calculate any type of solids or chemical in a flow or a volume. Um, so now the pounds formula does have some practical limitations. You're kind of assuming that the weight of all the substance is equal to the weight of water. And when you start getting really high amounts of solids, it almost kind of becomes meaningless. Like, say, for example, you had 500,000 milligrams per liter parts per million. That would mean half of your amount is the chemical or solids. So then the pounds formula is assuming kind of that everything weighs the same density as water, and it would kind of become ridiculous if you get a really high concentration of solids. So in that kind of in a wastewater situation, a lot of times what we do is we filter the solids that are in the liquid. We filter them out and weigh them, dry them and weigh them, and then we calculate the milligrams per liter that way. Uh, it can still be valid, but you'd probably take a different kind of approach for something with a lot of solids. I hope that answers the question. Did it sound like I was answering the right question, Owen?
Yeah, I think you were on the right track there. We're gonna get through a couple more, and then there's a couple longer-winded ones that I think I'm gonna send. I will send
Sure.
over to you afterwards,
Yeah.
and we'll get responses for. Um, so the next one was wondering, do you know what the source is for the table with the CT values at a pH of 10? I need to move.
Yeah, those are from EPA, from US EPA. Um, and that's a good caveat. I'm glad you brought that up because what you're going to want to do is you're going to want to use the compliance tables that are provided by your primacy agency. And it's likely, or it's possible, I should say, that the compliance tables that they're using on the state level might be slightly different than those general tables that I'm showing from EPA.
Awesome. I got two more for you. So someone was wondering, the CT, is that dose times contact time, or the residual times contact time?
That's good. Yeah, I see that. It's the residual. When you calculate the CT value, you measure the free residual after the process. So at the end of the contact basin, for example, you have a monitoring point. The dose isn't relevant in that you want the free residual that's still remaining after the process, because that's something you can depend on, because you might put a large dose and let's say every single bit of it gets used up by reducing compounds, it wouldn't be relevant. So you want to look at the residual, the free residual that's remaining. Good question.
I had one person wondering what the book was that you were talking about. It's the first question, that chemistry book.
Oh, that's a EPA manual that you can download for free from US EPA, and it's called the Arsenic Treatment Technology Handbook. And it's about arsenic technologies, but it has a nice section at the beginning that kind of explain some of those chemistry concepts for someone like myself who's not a chemist. And I thought it was good reading, and it explained a lot about the reactions that take place for oxidation and adsorption and lots of different technologies.
Awesome. And then I have two last questions that I believe are very similar. I'll read you both, and you can discern from that. So one says, why is 3-log removal harder to achieve than 4-log? It seems counterintuitive. And then someone else responded with chlorine disinfection by meeting 3-log Giardia inactivation. Sorry about that. Is 4-log viral inactivation met?
Yes, normally, yes, that's true. Why I say it's more difficult to achieve 3-log Giardia, you have a higher CT value that's required. From I've never seen it the opposite way. So when you achieve that 3-log Giardia, because Giardia is evidently a more robust organism, so it takes a higher CT value.
Okay, fantastic. There are longer form questions to everyone who's still here. Those longer form questions will be included when I send out the follow-up email. I just was going to wrap up and also say thank you for the presentation. It was very insightful. Someone did leave a comment saying that they came into this hoping to reinforce their knowledge, and you helped them to actually understand the formulas. So they were very appreciative of that. But with that, we will wrap up. So a huge thank you to Greg for sharing his expertise with us today. Following this webinar, you will receive a follow-up email with the slides from today and a link to the recording, as well as the questions. We also ask that you complete the webinar evaluation following the webinar so that you can let us know your thoughts on today's session, as it helps us plan for future webinars on topics that are important to you. Thank you again, and we hope to see you at future EFCN events.
Thank you, everyone.